Hello guys, this is Brett from STEM Tutors, and today we're going to talk about one of my favorite algorithms, and that's Huffman coding. I really enjoy this algorithm because it's very intuitive, something that you'll learn once here, and you'll never have to have someone explain it to you again. The general idea here is that we just reduce the number of bits used to encode the data, and it provides us with more efficient references into a static binary tree. Uh, and it boils down to just using frequency to sort a binary tree. So I think this will make more sense when you see it in action. I have an example prepared here. So in this example, we are provided with a string in which I've already counted up all the character frequencies, and we want to provide a Huffman coding. So the first step I like to do is rewrite the characters and their frequencies in a column from largest to smallest. You guys are going to see why we did this. So the steps in using to perform Huffman coding is that you want to start with, you want to keep combining your uh, lowest frequency roots. And let's see what I mean right now by that. So paired these, speed it up. So for instance, first of all, we have H and S. HS, these are 1, this is 1. So HS, cross them off. And I'm going to place HS, which is a 2, anywhere following the order of the stack, but I'll place it here. I find that if you place the subtree lower in your stack, not really a stack because we're pulling from the bottom, but in this column, you will get fewer trees and it'll make it a little bit easier, especially in a test situation where you're dealing with pencil and paper. So just a piece of advice there. But next let's move on to I and E. We have A, which is a 1, and we have HS and 2 or I and E. It doesn't really matter what we do as long as we take a 2 at the A. So I'm just going to add it right here. And there we are. Now we got to put it back in and cross off. We used I and E, and we used A. So you notice I didn't really take HS. Doesn't really matter. It's just you want to take the two smallest frequency values. In this case, those 2 and 2 are the same. So AIE is perfectly fine. And let's place it back in. And this one's a 3. Alright, now let's keep going. Now our next two smallest is HS and D. Alright, so moving up, now our next smallest is G and AIE. Okay. Now our next smallest is O and DHS. Alright, next smallest one is space and GAIE. So I'm going to do space to the left since it's smaller. Nine, and we used GAIE and space, and now we're at the last two, and now we just want to combine them. So 7 is smaller, so I'm going to keep that to the left. We've used all of them. And to encode it, you could choose either 0, 1, or you could do 1, 0. Doesn't really matter. We're concerned with the number of bits we're using, not the specifics, but I think convention would be 0, 1. So we'll stay with that. 0. Every time we go left, we write a 0. 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0. So I'm going to encode just a couple, just so you get the idea. So for instance, I think a good comparison would be two that are very far apart in frequency. So let's do A and space. So where is A at? Here it is. So A, we have to go 1, 1, 1, 0. So A's encoding would be 1, 1, 1, 0. Now what about space? It should be less, and if it's not less, you probably did something wrong. So let's look. There it is, okay. So here's space right here, so it's going to be 1, 0. There we go. In the next video, we'll go over how to actually encode this sentence with the encoding that we're going to produce. So I'll see you in the next video. Thanks.